The air in the workshops of Britain in the mid-19th century hummed with a revolutionary sound, the ceaseless thrum of steam engines. These colossal machines, the very pulse of the Industrial Revolution, were transforming the world, driving factories, propelling trains, and forging empires. But beneath their powerful, rhythmic beat, an unexpected and profound realization was slowly taking hold, not just about the efficiency of machinery, but about the ultimate fate of everything. This was not an astronomical discovery unveiled by distant telescopes, but a concept of cosmic death forged in the very fires of human ingenuity, born directly from the ambition to understand and optimize these powerful new engines. At the forefront of this conceptual shift was a man of towering intellect and deep faith, William Thomson, later known as Lord Kelvin. In the 1850s, Kelvin, a brilliant physicist and engineer, was among the first to formalize the revolutionary laws of thermodynamics. These laws were initially conceived to maximize the output of steam engines, to squeeze every last joule of useful work from a lump of coal. Yet, Kelvin possessed a mind that saw beyond the factory floor, extrapolating these very earthly principles to the vast, incomprehensible cosmos. He turned his formidable intellect to the sun, our life-giving star, attempting to calculate its lifespan. In his original papers, a fascinating tension emerges. Kelvin theorized that the sun shone not through some infinite mystical power, but through the slow gravitational collapse of its own mass. His calculations, based on the known laws of physics at the time, suggested a surprisingly short lifespan for our star, perhaps only 20 million years. This was not a purely scientific pursuit. His work was deeply intertwined with his theological desire to refute Charles Darwin's increasingly popular theory of evolution, which seemed to demand timescales far grander than Kelvin's dying sun could allow. The universe, in Kelvin's eyes, was a grand divine clock, meticulously wound but undeniably running down. Then, in 1865, the German physicist Rudolf Clausius introduced a term that would forever alter our perception of the universe's end: entropy. Clausius starkly declared that while the total energy of the universe remains constant, it can neither be created nor destroyed. Its entropy, or disorder, is relentlessly increasing, always tending toward a maximum. This irreversible march toward disorganization, he concluded, would inevitably lead to a state he chillingly termed Wehrmethod, or heat death. This was not merely a theoretical construct. It painted a cosmic picture where all usable energy would eventually dissipate, all differences in temperature would vanish, and the universe would settle into a uniform, stagnant, eternally cold equilibrium. This concept of heat death was far more than a dry scientific theory. It rapidly permeated the cultural consciousness of the era, becoming a potent symbol of decline and decay. It infused the pessimistic philosophy of figures like Oswald Spengler, whose monumental work, The Decline of the West, echoed the universe's inevitable entropy in its analysis of civilizational collapse. One can trace its dark romanticism through the literature of the age, where narratives often depicted worlds fading into gloom, echoing the universe's supposed entropic demise. We find chilling reflections of this in archival letters from the period, where intellectuals and laypeople alike grappled with this newfound cosmic prognosis. Their correspondence reveals a widespread public anxiety, a form of existential dread that was entirely new to humanity, a creeping fear that even the cosmos itself was not immune to the fate of a fading flame. This first glimpse we had of the universe's ultimate demise was, in essence, a reflection of our own nascent technology. The cosmos was no longer seen as an eternal, unchanging realm, but rather as a vast cosmic engine. And like any engine, particularly those powering the factories of Victorian Britain, it needed fuel. The heat-death scenario proposed that the universe was simply running out of its cosmic coal, its usable energy slowly, inexorably, dwindling to nothing. This profound, technologically inspired vision of the end of all things set the stage for every future reimagining of our eschatological visions, a dark blueprint upon which generations of scientists and thinkers would build, each new technological and theoretical shift reshaping our understanding of how our world, and indeed all worlds, might finally cease to be. The cosmos, once a vast, eternal stage, had, by the dawn of the 20th century, begun to feel like a grand, meticulously wound clock, undeniably running down. The chilling specter of heat death, a universe destined to fade into an unending, frozen equilibrium, had settled over scientific thought like a shroud. This was the universe as seen through the lens of Victorian thermodynamics, a cosmic engine simply running out of coal, promising an ultimate, claustrophobic end. But then, a monumental shift began to stir, a profound reimagining that would not only offer a temporary reprieve from this inevitable cold fate, but would paradoxically reveal an even grander, more isolating destiny. The year was 1929, and high above the bustling streets of Pasadena, California, at the Mount Wilson Observatory, a lone figure stood at the eyepiece of the 100-inch Hooker telescope. This was American astronomer Edwin Hubble, a man whose observations were about to revolutionize humanity's place in the universe. With the Hooker, then the most powerful telescope in the world, Hubble was meticulously studying distant galaxies, not just photographing their ethereal beauty, but measuring their precise distances and, critically, their velocities. What he found was nothing short of astonishing. Almost every galaxy he observed was hurtling away from us, and the farther away it was, the faster it receded. This was the definitive observational evidence. The universe was not static, it was expanding. Yet, like many profound scientific breakthroughs, the observational confirmation often stands on the shoulders of unsung theoretical giants. Years before Hubble peered through his telescope, the theoretical groundwork for a dynamic cosmos had already been laid. Consider the work of Russian mathematician Alexander Friedmann. In 1922, grappling with Albert Einstein's complex equations of general relativity, Friedmann mathematically predicted a universe that was not static, but instead either expanding or contracting. His groundbreaking papers, published in a relatively obscure German journal, went largely unnoticed by the wider scientific community, a testament to how ahead of his time he truly was. Then, independently, in 1927, a Belgian priest and physicist named Georges Lemaitre arrived at a similar conclusion. Lemaitre, often called the father of the Big Bang, not only proposed an expanding universe from his own work on general relativity, but also put forward the radical idea of a primeval atom, a tiny, incredibly dense state from which the entire cosmos had begun. His insights were so profound, yet initially met with such staunch resistance, particularly from the era's most celebrated mind. Even Albert Einstein, the very architect of general relativity, struggled with the implications of a dynamic universe. His equations seemed to naturally point towards expansion or contraction, but a static, eternal cosmos was the prevailing philosophical and scientific expectation of the time. To force his universe into a state of unchanging equilibrium, Einstein famously introduced what he called the cosmological constant into his equations, an arbitrary fudge factor designed to counteract gravity and keep the universe from collapsing or expanding. It was a theoretical bandage over a wound he didn't want to acknowledge. Years later, after Hubble's irrefutable evidence, Einstein himself, with characteristic candor, would call this cosmological constant his biggest blunder. Simultaneously, another crucial scientific puzzle was being solved, one that offered a more immediate reprieve from the grim forecast of heat death. The very same era that saw the discovery of cosmic expansion also witnessed a breakthrough in understanding the engine of stars, nuclear fusion. Scientists realized that stars like our Sun were not simply burning down a finite supply of chemical fuel or slowly collapsing as Lord Kelvin had once theorized. Instead, they were colossal, self-sustaining nuclear reactors, converting hydrogen into helium at their cores, releasing gargantuan amounts of energy in the process. This discovery meant that stars could shine for billions, even tens of billions of years, fundamentally solving Kelvin's problem of a short-lived sun. It was as if the universe had revealed an infinite gas tank, pushing the specter of a cold, dark end far into the unimaginable future. Yet, this great escape came with its own profound, and perhaps even more unsettling, truth. The expanding universe, while seemingly offering near-infinite time and space, also fundamentally transformed our cosmic address. No longer were we nestled on a cozy, static island, surrounded by a universe that was ultimately fixed and knowable in its boundaries. Instead, our Milky Way galaxy, containing hundreds of billions of stars, became a single raft adrift on an endlessly growing, emptying ocean. This cosmic expansion, far from being a simple reprieve, introduced an entirely new and more profound set of questions about our ultimate solitude and fate. What did it mean to be a tiny speck in a cosmos that was not merely vast, but actively pulling itself apart, leaving ever more space between its scattered islands of matter? We have peered into cosmic engines slowly running out of coal, imagined immense canvases stretching into an empty, lonely void, and even contemplated a universe violently torn asunder. But what if the ultimate end of all things is not a matter of heat or space, but something far more fundamental, something tied to the very essence of how reality is structured and how we ourselves organize our knowledge? What if the universe's true demise is not thermal, but informational? This unexpected turn in our cosmic narrative takes us back to the late 1870s, to the foundational and, at the time, deeply controversial work of an Austrian physicist named Ludwig Boltzmann. Before Boltzmann, entropy was primarily understood as wasted heat, a measure of how much energy in a system became unavailable for work. It was an engineering concept born from the steam engines that hummed across industrial Europe. But Boltzmann, with revolutionary insight, dared to redefine it. He saw entropy not just as dissipated energy, but as a measure of microscopic disorder, a statistical property of atoms. For him, the universe wasn't just losing heat, it was losing order, its constituent particles arranging themselves into an ever greater number of chaotic configurations. His ideas were met with fierce resistance from many who doubted the very existence of atoms, but his vision would prove prophetic. Fast forward to 1948, and the bustling, innovative Bell Labs offices in New Jersey. Here, an American mathematician named Claude Shannon, the father of information theory, was laying the groundwork for the digital age. He was grappling with the fundamental problem of how to transmit and store data efficiently and reliably. Shannon developed equations to measure information, quantifying it in what he called bits, the fundamental unit of digital data. A single bit, a choice between two possibilities like 0 or 1, holds a tiny piece of information. Here lies the startling, non-obvious parallel. If one examines Shannon's equations for measuring information in bits and compares them to Boltzmann's formula for entropy, they are mathematically almost identical. This profound congruence suggests something far deeper than mere coincidence. It hints at a startling idea. The universe itself can be seen as a colossal information processing system. From this perspective, the second law of thermodynamics, that seemingly inescapable march towards maximum entropy, is essentially a law of progressive data corruption. The universe is not just cooling down, it is forgetting itself, its intricate structures slowly dissolving as the information needed to build and maintain them gets irretrievably lost. This concept faces its ultimate stress test in one of the most enigmatic objects in the cosmos, the black hole. Championed by the brilliant British theoretical physicist Stephen Hawking, the black hole information paradox asks a terrifying question. What happens when information falls into a black hole? Classical physics suggests anything crossing the event horizon is lost forever, crushed into a singularity, and thus its information is destroyed. But quantum mechanics dictates that information can never be truly lost. It must always be conserved. The thought that information could vanish into a black hole created a profound conflict, a fundamental breakdown in our understanding of physics that fueled decades of intense debate. If a book falls into a black hole, does the story it contains simply cease to exist? This paradox forces us to confront whether the universe truly remembers everything. The physical link between information and entropy was further illuminated in 1961 by the German-American physicist Rolf Landauer. His principle established a crucial connection. Erasing a single bit of information necessarily generates a tiny but measurable amount of heat. Think of it. Every time a computer deletes data, or a system forgets its past state, it adds a minuscule quantity of energy, a minuscule amount of disorder, to the universe. This means that the very act of any system losing information, of its past becoming unrecoverable, directly increases the universe's total entropy. The more things forget, the faster the universe decays. Therefore, the ultimate end might not be a cold, dark place where all energy is uniform, but a state of maximum entropy where no complex structures can possibly exist because the universe has simply lost all the information required to build them. Imagine a computer hard drive, once filled with vibrant programs and intricate data, slowly degrading until every bit is a randomized, meaningless mess. No operating system could boot, no image could be rendered, no thought could be formed. The cosmic ledger would be wiped clean, not by fire or ice, but by the relentless, irreversible erasure of all meaningful data. The cosmos, as we understood it for so long, seemed destined for a slow, dignified fade. Gravity, that universal glue, was supposed to be tugging at the fabric of space, gradually decelerating the expansion set in motion by the Big Bang. Every major cosmological model, every careful calculation, pointed to this eventual cosmic slowdown, promising a long, if perhaps cold, drift into the distant future. But in the late 1990s, a seismic shift occurred, not in the distant reaches of space, but within the very fabric of our understanding, completely upending this predictable narrative. At the heart of this revolution were two rival teams of astronomers, locked in a quiet, intense race. One group was led by Saul Perlmutter at the Supernova Cosmology Project, and the other, the High Z Supernova Search Team, by Brian Schmidt and Adam Rees. Their mission seemed straightforward: use distant supernovae as standard candles to measure how fast the universe's expansion was slowing down. These particular stellar explosions, known as Type 1a supernovae, are incredibly bright and consistent in their peak luminosity, much like a specific wattage light bulb visible across vast distances. By measuring their apparent brightness, scientists could precisely determine their distance, and by analyzing the redshift of their light, ascertain how quickly their host galaxies were receding. The goal was to chart the universe's deceleration over billions of years. What they found, however, was not the anticipated slowdown. It was the exact opposite. To the shock of both teams, independently verified and announced in 1998, the universe was not decelerating. It was accelerating. Distant supernovae appeared fainter than expected, implying they were farther away than their measured redshift alone would suggest, meaning the space between us and them was expanding at an ever-increasing rate. This discovery was so profound, so utterly unexpected, that it baffled the scientific community and reshaped cosmology overnight, ultimately earning Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It was as if the universe had slammed on the accelerator pedal rather than the brakes. This startling revelation completely upended previous cosmological models, transforming the slow, dignified fade of heat death into a new, terrifyingly violent possibility. The universe was no longer a cosmic engine simply running out of coal, slowly winding down into eternal slumber. Instead, it was as if an unknown, anti-gravitational force, dubbed dark energy, had suddenly appeared, pushing galaxies apart with ever-increasing ferocity. This mysterious entity, making up an estimated 68% of the universe's total energy content, acts as a sort of cosmic anti-gravity, stretching space itself faster and faster. Its nature remains one of the greatest mysteries in modern physics, a phantom presence dictating the ultimate fate of all existence. One of the most extreme and chilling scenarios born from this discovery is the Big Rip hypothesis, first formulated in detail by Dr. Robert Caldwell of Dartmouth College in 2003. This terrifying concept suggests that if the repulsive force of dark energy continues to grow stronger over time, specifically if it takes the form of what physicists call phantom energy, a theoretical substance with peculiar properties, it will eventually overcome every other fundamental force in the cosmos. Imagine a cosmic tug-of-war, where the invisible pull of dark energy steadily increases its strength, overwhelming the very bonds that hold everything together. The timeline for such an event is vast, yet disturbingly precise in its escalating violence. Billions of years from now, the growing influence of dark energy would first begin to tear apart the largest structures in the universe. Galaxy clusters, immense collections of thousands of galaxies like the Virgo cluster, stretching tens of millions of light-years across, would be ripped asunder, their constituent galaxies flying away from each other at incredible speeds. Then, our own Milky Way galaxy, a majestic spiral spanning 100,000 light-years and containing hundreds of billions of stars, would be next. Its spiral arms would unbind, stars would scatter, and our sun, once a member of this grand cosmic ballet, would find itself alone in an increasingly empty void. Further down the timeline, in the final stages of this cosmic annihilation, the Big Rip would target individual solar systems. The gravitational bonds holding our Earth in orbit around the Sun, a force of roughly 3.5 times 10 to the 22nd newtons, would fail. Our planet would be flung into the cold, dark emptiness, followed by the complete disintegration of the solar system itself, its planets, asteroids, and comets ripped away from their star and from each other. But the horror does not end there. In the frantic final minutes, possibly less than an hour before the ultimate end, the repulsive force of dark energy would become so overwhelmingly powerful that it would overcome the electromagnetic forces holding our planet and our bodies together. Picture this: the very atoms that compose your hand, the desk before you, the air you breathe, would be stretched and pulled apart. Electromagnetic forces, which bind electrons to atomic nuclei with energies measured in electron volts, would be insufficient to resist the accelerating expansion of space itself. Protons and neutrons, the building blocks of atomic nuclei, held together by the strong nuclear force, the most powerful of the four fundamental forces, would be next. This force, 1,000,000 times stronger than the electromagnetic force, would finally succumb, tearing nuclei apart. Ultimately, even the quarks and gluons, the subatomic particles that make up protons and neutrons, would be ripped from each other, reducing everything in the universe to a soup of elementary particles flying infinitely apart. This chapter frames dark energy not as a gentle force of cosmic separation, but as the ghost in the machine of the cosmos, an unknown variable that has transformed our understanding of the universe's end from a predictable, albeit cold, decline into a high-stakes thriller with a potentially explosive finale. The universe has offered us many grand, terrifying finales. We have witnessed the slow, inevitable fade of heat death, where all usable energy dissipates into a uniform, stagnant cold. We have contemplated the cosmic ledger being wiped clean, all information dissolving into meaningless static. And we have even shuddered at the thought of a Big Rip, where an unseen force relentlessly tears apart galaxies, stars, and even the very atoms of our bodies. But what if the greatest threat to our existence comes not from a slow, grinding process or a violent explosion, but from something far more subtle, a fundamental instability embedded within the very fabric of reality itself? What if the ground beneath our cosmic feet is not as solid as it seems? This unsettling possibility is rooted not in the grand scales of cosmology, but in the bizarre, counterintuitive realm of quantum field theory. It introduces the concept of the vacuum state, which might sound like nothingness, but in physics, it refers to the lowest possible energy level of empty space. Every fundamental field in the universe, from the electromagnetic field that carries light to the Higgs field that gives particles mass, has a vacuum state. It is the baseline, the ultimate bedrock upon which all of reality is built. The terrifying hypothesis then emerges. What if our universe is not, in fact, in its true vacuum state? What if it is merely residing in a false vacuum? This idea, seemingly pulled from the pages of science fiction, was rigorously explored by theoretical physicist Sidney Coleman at Harvard University in the late 1970s. His groundbreaking calculations showed that our universe might be what physicists call metastable. To grasp this concept, consider a droplet of supercooled water. It remains liquid even below its freezing point, poised precariously, waiting for the slightest disturbance, a dust particle, a tiny vibration, to instantly transform it into solid ice, releasing a burst of energy as it snaps into its true lower energy state. Our universe, according to Coleman's work, could be in a similar, profoundly unstable condition. To better understand this, picture the universe as existing in a valley, representing its current energy state. It feels stable, comfortable. But what if, just over a high mountain range, there lies an even deeper, more stable valley? This deeper valley would represent the true vacuum state, a configuration of fundamental fields with an even lower energy level than our own. Normally, for our universe to roll into that deeper valley, it would need an enormous amount of energy to climb over that mountain barrier. It is a barrier so vast, so insurmountable, that it should, in classical physics, forever protect our current reality. However, the universe is governed not just by classical physics, but by the enigmatic laws of quantum mechanics. And here, a phenomenon known as quantum tunneling enters the picture. Quantum tunneling is a proven phenomenon on a small scale. Subatomic particles, for instance, can seemingly tunnel through energy barriers that they classically shouldn't have enough energy to overcome. It is a bit like a ball spontaneously appearing on the other side of a solid wall, without ever having gone over or through it in the classical sense. This quantum weirdness, scaled up to the cosmos, suggests there is a non-zero, albeit minuscule, probability that a tiny patch of our universe could spontaneously tunnel through that cosmic mountain into the true vacuum state. Should this unfathomable event occur, it would not be a slow, gradual change. It would unleash a catastrophic cascade. A bubble of this true vacuum would spontaneously nucleate somewhere in the universe, an infinitesimal point where the fundamental laws of physics would abruptly rewrite themselves. This bubble would then expand outwards at the ultimate cosmic speed limit, the speed of light. Nothing, absolutely nothing, could outrun it. As this true vacuum bubble washes over everything in its path, stars, galaxies, planets, and even the empty space between them, it would obliterate all existing structures. The fundamental forces we know, the very particles that make up matter, might cease to exist as they are, transforming into something utterly alien and unrecognizable. For decades, this remained a theoretical curiosity, a truly unsettling, yet perhaps distant, possibility. Then, in 2012, a monumental discovery at the Large Hadron Collider, LHC, in Switzerland, provided crucial, tangible data for these calculations. The long-sought Higgs boson was finally detected. This particle is inextricably linked to the Higgs field, which permeates all of space and gives other fundamental particles their mass. The precise measurement of the Higgs boson's mass, a value of approximately 125 giga-electronvolts, when plugged into the equations for vacuum stability, placed our universe in a critically metastable region. This does not mean it is guaranteed to happen tomorrow, or in a billion years, but it renders the scenario unnervingly plausible. The universe, in this vision, is living on borrowed time, like a house of cards that could collapse with the slightest, unpredictable quantum tremor. The end, if it arrives this way, would not be a slow astronomical process stretching across eons, but an instantaneous, unpredictable event, a cosmic phase transition that we could never see coming. We have witnessed cosmic finales of fire, ice, and ultimate dissolution, each vision a chilling reflection of humanity's evolving understanding of the universe. But as the cosmos inexorably ages, as stars dim and galaxies drift apart, a profound, almost defiant question emerges from the depths of human curiosity. Can life itself, can intelligence, somehow defy the physics of the end? Can consciousness outlast the very universe that spawned it, perhaps for aeons beyond the death of the last star? It was in 1979 that the brilliant theoretical physicist Freeman Dyson, a man known for his wildly imaginative yet rigorously scientific ideas, dared to challenge the apparent inevitability of intellectual death. In his groundbreaking paper, Time Without End, Physics and Biology in an Open Universe, Dyson posited that a sufficiently advanced civilization, facing a universe cooling toward the ultimate heat death, might not simply vanish. Instead, he argued, such a civilization could survive for literally infinite time, adapting to the ever-decreasing energy supply by adopting radical strategies. One such strategy involved intermittent hibernation. Imagine a civilization designed to operate in brief bursts of intense activity, perhaps for 1,000,000 years, consuming all available energy, then shutting down for 1,000,000,000,000 years, waiting for the universe to expand and cool further, allowing for new energy gradients to form. Their thoughts, their very computations, would be structured to require progressively less energy per unit of information, becoming ever more diffuse and slow, but never ceasing entirely. Dyson's concept of eternal life was not a biological state of perpetual youth, but rather a state of perpetual information processing, a continuous, albeit increasingly languid, flow of thought that could stretch across unimaginable cosmic timescales. This links directly to the idea we have explored earlier, the universe as an information system, and the ultimate death of the cosmos as the death of information. Yet, Dyson's remarkable optimism, while compelling, must contend with the stark and unforgiving physical constraints imposed by the laws of thermodynamics. As the universe continues its inexorable march towards maximum entropy, useful energy becomes ever scarcer. A truly advanced civilization would need to become master harvesters of every last vestige of energy. Consider the iconic concept of a Dyson sphere, a megastructure encompassing an entire star, capturing nearly 100% of its radiant energy output. Around a sun-like star, such a sphere could potentially capture a staggering 4 times 10 to the power of 26 watts, an energy flow roughly a billion times greater than humanity's current total power consumption. Even as stars die, becoming white dwarfs or neutron stars, these colossal structures could still glean residual heat for eons. But what happens when even the last dying embers of stars fade? The ultimate energy source in a collapsing universe might lie within the most enigmatic objects, black holes. The Penrose process, a theoretical mechanism proposed by Roger Penrose, describes how energy could be extracted from the rotation of a spinning black hole. By carefully dropping matter into the black hole's ergosphere, a region where spacetime itself is dragged around by the hole's rotation, and then ejecting a portion of that matter, it is possible to extract rotational energy. This process could theoretically harness a significant fraction of a black hole's rotational energy, perhaps up to 29% of its total mass energy, offering a powerful, albeit exotic, energy well for a civilization clinging to existence billions upon billions of years in the future. This brings us to the ultimate metabolic limits of computation and thought, as defined by the very laws of physics. The Landauer principle, a cornerstone of information theory, states that erasing a single bit of information necessarily dissipates a minuscule but unavoidable amount of energy into the environment. This minimum energy, known as the Landauer limit, is proportional to the temperature of the system. In a universe ever cooling towards absolute zero, the energy cost per computation would decrease, theoretically allowing more computation for the same amount of energy. Could a disembodied superintelligence, existing not as a biological entity but as pure information, encode itself on ever lower energy particles, its thoughts slowing down but never truly stopping, adapting to temperatures approaching absolute zero, perhaps just a few billionths of a degree Kelvin above the cosmic background? Or is the ultimate heat death, the death of information itself, an insurmountable barrier? As entropy relentlessly increases, as all meaningful information is irretrievably lost, will even the most advanced consciousness eventually dissolve into the silent, random static of the final void? This is no longer merely an abstract physical prediction. It transforms the very end of the universe into a deeply personal struggle, a cosmic race for the survival of consciousness itself. Across the vast, sprawling timeline of human history, one question has consistently haunted our collective consciousness: how will it all end? For centuries, the answers were etched in mythologies and prophecies, stories spun by shamans and prophets. But as humanity delved deeper into the crucible of scientific inquiry, our visions of the universe's ultimate demise transformed, each new theory not merely a prediction, but a profound mirror reflecting the very era that conceived it. The dawn of the scientific age brought with it the chilling specter of heat death, a cosmic fate born from the roaring furnaces and intricate gears of the 19th century's Industrial Revolution. This was a time obsessed with engines, with efficiency, and with the inevitable decay of mechanical systems. It felt logical, almost comforting, to conceive of the universe as a grand, meticulously crafted machine, destined to simply run out of its cosmic fuel. The inexorable march towards a uniform, cold equilibrium where all usable energy would dissipate was the universe's version of a grand clock winding down, its intricate mechanisms finally ceasing their elegant dance. It was a reflection of the anxieties inherent in an age that had mastered the steam engine, yet also understood its finite limits. Then, as the 20th century roared to life, marked by unprecedented speed and acceleration, by the rise of global communication and increasingly rapid technological change, our cosmic fears accelerated too. The discovery of dark energy, that mysterious, anti-gravitational force pushing galaxies apart with ever-increasing ferocity, unleashed the terrifying possibility of the Big Rip. No longer a slow, dignified fade into the cold, the universe could instead be destined for a violent, explosive finale, ripped apart at every scale, from galaxy clusters down to the very atoms of our bodies. This was the universe as seen through the lens of an age grappling with ever faster travel, with the dizzying pace of progress, and with the unsettling realization that some forces, like the cosmic expansion itself, were utterly beyond our control. It spoke to a deep-seated anxiety about runaway systems, about forces that, once unleashed, could not be contained. As the digital age enveloped us, reshaping how we store, transmit, and perceive information, our understanding of cosmic death gained an entirely new, more abstract dimension. The concept of informational death emerged, suggesting that the true demise of the cosmos might not be thermal, but rather a relentless erasure of data. This was a fear born in a world where the loss of data, a corrupted hard drive or a wiped server, could be catastrophic. If the universe itself is a colossal information processing system, then its ultimate end might be less about a physical collapse and more about a complete, irreversible loss of all meaningful structure and complexity, a cosmic ledger wiped clean until no thought could be formed, no star could coalesce, because the information to build them had simply dissolved into static. And finally, from the strange, counterintuitive realm of quantum mechanics, a concept emerged that truly embodied the 21st century's embrace of uncertainty and probability, the false vacuum decay. This vision suggests our universe might be balanced precariously on a knife edge, in a metastable state, like a droplet of supercooled water waiting for the slightest disturbance to instantaneously freeze. This idea, where a tiny, unpredictable quantum tremor could trigger a cosmic phase transition expanding at the speed of light, obliterating everything in its path and rewriting the fundamental laws of physics, is a quintessential quantum age concept. It emphasizes the deep, unsettling reality that the most profound changes can occur without warning, driven by probabilities beyond our direct perception, leaving us utterly powerless to foresee or prevent them. What all these shifting eschatological visions reveal is a profound truth. Our quest to understand the universe's end is intrinsically linked to solving the greatest remaining mysteries in physics. The true nature of dark energy, the very force driving accelerated expansion and potentially the Big Rip, remains one of the most enigmatic questions. How does it work? Is it constant, or does it change? Its ultimate behavior will dictate the final chapters of our cosmic story. Then there is the elusive dream of unifying gravity with quantum mechanics, a grand theory of everything that would reconcile the vastness of the cosmos with the bizarre realm of the subatomic. Such a theory might reveal whether our vacuum state is truly stable, or if the universe is indeed a house of cards waiting for an unseen quantum wind. And finally, the black hole information paradox, a puzzle that forces us to confront whether information can truly be lost, holds the key to understanding if the death of data is the ultimate, insurmountable barrier to cosmic complexity and even consciousness. We do not possess a definitive answer to how it will all end. The universe is a far more intricate and mysterious tapestry than any single theory can fully describe. But the very pursuit of that answer, the relentless drive to peer into the furthest reaches of time and space, is not merely an academic exercise. It is, in essence, the very same quest to understand its beginning, its fundamental laws, and the ultimate rules of this reality. For the answer, if we ever find it, will not just tell us about our distant future, about the eons that stretch beyond our comprehension. It will fundamentally redefine our understanding of our existence, right here, right now, revealing the deepest nature of the stage, upon which all life, all consciousness, and all wonder unfolds.